Mic check, mic. Hi, I'm Terry, better known as Mr. White Keys, and thank you for joining today. Today we're going to start off a series of videos talking about Project 2026, the ultimate computer glasses build. Now, if you spend your life anchored to a multi-monitor workstation, you're already paying the daily tax. You know the drill. The burning eyes by mid-afternoon, that stiff neck, and that subconscious chin raise just to keep a line of code or a technical diagram or a video frame in focus. For office professionals, YouTube creators, and the modern digital workforce, we've silently accepted a flawed paradigm. We suffer through heavy frames that pinch and slide. We settle for mass-produced lenses derived from subjective, close enough eye exams. You know that one, which is better, one or two or about the same? And I can never figure out the answer to those questions because half the time they look the same to me. But in any case, that is based on a century-old process that's tied to manufacturing limitations for grinding glass lenses from 100 years ago. One that completely ignores the microscopic objective reality of your own eyes. We're told this is just part of the job, a mandatory price for a modern life. Now, as an eyewear enthusiast, I have plenty of fashionable progressives, single vision computer glasses, and prescription sunglasses. But while hunched over in front of my computer, I realized something. I spend most of my waking hours locked into a highly demanding digital environment. I no longer just need glasses. I need a precision optical instrument capable of sustaining an intense multidisciplinary digital workflow. But what if the pain that we're feeling isn't an ergonomic failure, but actually an optical engineering failure? And more important, what if it doesn't have to be that way? What if there is a better way? This is Project 2026. We aren't just building computer glasses. We're manufacturing a highly customized biometric prosthesis. Over the course of this series, I'm going to show you a repeatable, precision workflow to completely eradicate screen fatigue. We're using the IoT Digital Ray Path 2 compute engine and the brand new Chromatic Aberration reduction technology, or CART color science technology, carved onto a Trivex Camber blank to create a Camber Pure Office Progressive with a 1.3 meter configuration. This technology is literally hot off the proverbial lab software press. Every single metric, from the modular comfort of the frame and the precise mapping of your facial geometry to the high-order telemetry of your ocular topology and the computational engine carving the lens itself, is built specifically around you. I'm embarking on a journey to completely redefine the bespoke optical instrument, and if you too work under the shadow of a wall of monitors tethered to a desk for long hours every day, I want to take you with me. Together, we're going to take office eyewear to the next level. Get ready for some fun and come with me as I build a Hubble telescope for my face. This isn't just one video. To do this right, we have to deconstruct the entire stack, and we're going to split this journey into 11 episodes broken up into 2 parts. Act 1 is the blueprint. In episode 1, that's the project charter. That's where you are right now. This video is about the project charter. Episode 2 is the chassis, decoupling facial geometry with radical modularity. Episode 3 is the hardware, exploring variable base curves and the elephant trunk profile of the IoT Camber blank. Episode 5 is surgical telemetry, harvesting over 14,000 data points with a Nidek laser scanner. Episode 5 is the engine. We'll talk about the computational physics using the Digital Ray Path 2 and color aberration reduction technology, color science. Episode 6 is the synthesis. This is where it all comes together. This is where the magic happens, where the lab merges your biology into the plastic. And then in Act 2, we're going to leave the studio. I'll take you inside one of the country's premier eye clinics, into the fitting chair with a master optician, and finally through the unboxing and the 30-day verdict. So let's talk about the physical foundation and overcoming frame fatigue. Standard, off-the-rack frames are fundamentally flawed for prolonged workstation use. When a frame is not customized to exact facial dimensions, it becomes a physical burden. Heavy frames create pressure points, pinching the bridge of the nose and cutting into the mastoid bone behind the ears. Worse, poor weight distribution causes the glasses to feel front heavy and continuously slide down the nose. And in optics, even a millimeter of vertical shift alters the optical center, forcing the eyes to look through an unoptimized portion of the lens, which immediately induces eye strain. Now, frames from Götti of Switzerland, the Perspective collection, solve this through radical modularity. Launched in 2016, they offer over 38 basic, highly modifiable lens shapes that form the foundation of a highly modular, custom-made collection of frames featuring modular rims and over 14 interchangeable colors and a variety of custom dimensions. As an ultra-lightweight, rimless-based chassis with a 3D printed bold rim additive, it allows for a decoupled approach to facial geometry. Rather than accepting a fixed unit, the bridge width, temple length, and lens size can be independently selected and physically bent to spec. Splayed nose pads distribute weight flawlessly, while a precise temple drop grips the head perfectly, ensuring the lens remains locked into the exact position of wear required to keep a multi-monitor setup sharply in focus all day long. I selected the DC02 frame in the bold configuration with the ruby colorway with polished gold temple arms. Now let's talk about the Optical Foundation, the limitations of standard lenses. The traditional approach to computer glasses utilizes a single vision lens with a fixed focal distance. This forces the user into a rigid physical posture, leaning in or out to keep the various monitors in a multi-monitor setup in focus, which rapidly leads to neck and shoulder fatigue. Furthermore, a single vision lens cannot accommodate the dynamic reality of a modern workplace. An office progressive lens, on the other hand, provides a seamless depth of field, a continuous focal corridor that allows the eyes to transition smoothly from a keyboard to a primary monitor and out to secondary displays, all without physical head movement. The 1.3 meter IoT office progressive lens eliminates the severe postural strain caused by the traditional optics in multi-monitor setups. Single vision lenses lock focus to one depth, forcing users to constantly lean forward and backward between their keyboard and the screens, which drives neck and shoulder fatigue. Standard progressives are equally unviable. Their narrow intermediate corridor requires continuous head turning to clear peripheral blur of the side monitors. Furthermore, because this intermediate zone is positioned too low in the lens, wearers are forced into a painful, exhausting chin raise just to keep the displays in focus. Now try doing that for the entire workday, right? By utilizing a deliberate 1.3 meter digression, which is about 51 inches, the IoT Office Progressive lens dedicates its entire geometric canvas strictly to the immediate environment. It constructs a massive, ultra-wide visual corridor that perfectly envelops the deep spatial topology of the desk, allowing the eyes to effortlessly sweep from a video editing console across a wall of monitors in razor-sharp focus without requiring a single compensatory head or chin lift. Now, the glass. Most premium lenses from Zeiss or Essilor start with a generic puck. It's a flat cylinder of plastic. This forces the CNC lathe to carve every variable, your prescription, your astigmatism, and most demandingly, your reading power, all onto the back surface of the lens. This is what we call a brute force approach that essentially breaks the math. This is where we get into the Minkwitz theorem. It states that as magnification increases, peripheral distortion multiplies. By forcing everything onto one surface, you choke the visual corridor, forcing that painful chin raise to find a tiny sweet spot. Project 2026 uses the IoT Camber blank. It features a patented elephant trunk profile on the front surface, a curve that continuously steepens toward the bottom. By molding the reading power onto the front, we offload this heavy lifting. The CNC lathe is then liberated to focus entirely on smoothing out transition zones and widening corridors. We're building for a specific 1.3 meter digression. This lens doesn't care if you see a clock across the room. It's dedicated 100% to your 51-inch workstation canopy. By physically building the reading addition into the front geometry of the blank, the eye is granted significantly more reading room. The calculation engine is then freed from brute force magnification duties, allowing it to focus entirely on smoothing out the peripheral zones. By offloading this heavy optical lifting to the front of the blank, the calculation engine is liberated. It no longer has to struggle to generate reading power on the back surface. Instead, the engine can dedicate its entire processing capability to smoothing out the peripheral zones and customizing the optical pathways. For the patient, the decision to build a progressive lens on an IoT Camber blank rather than a standard uniform puck translates into an immediate, highly observable expansion of usable vision. When accommodating a dense plus 2.5 reading addition, this architectural advantage is profound. The patient experiences a dramatic reduction of the swim effect at the edges of the frame and gains a massively widened, distortion-free near zone, allowing for a natural, relaxed visual sweep across a wide editing console and an array of monitors that a standard lens simply cannot physically provide. Now let's talk about data acquisition, the Nidek OPD Scan 3 versus the subjective exam. An elite lens requires elite telemetry. The standard subjective optometry exam asking which is better, 1 or 2 or about the same, yields a prescription rounded to the nearest quarter of a diopter. This approximation ignores the microscopic reality of the eye. The diopter system was pioneered in 1866 by German ophthalmologist Albrecht Nagel, who numbered lenses based on the reciprocal of their focal length in meters. And then it was formalized and named diopters by French ophthalmologist Ferdinand Monnier in 1872. Then the optical industry had to decide on the intervals between lens powers. The decision to standardize the quarter diopter increment is largely driven by the limitations of the late 19th and early 20th century, during which time a quarter of a diopter was the limit of their ability to produce lenses in what was essentially an entirely physical, mechanical process. Supplementing clinical refraction with the wavefront aberrometry of the Nidek OPD Scan 3 changes the paradigm. The Nidek acts as a 5-in-1 workstation, capturing 2,520 data points across the visual pathway. Instead of relying purely on a subjective guess, it measures high-order aberrations, monocular pupillometry in both mesopic and photopic conditions. Mesopic is dim conditions and photopic is a bright condition. And then precise S1 wavefront values describing the Zernike order 1 total tilt for each eye. This yields a prescription accurate to 100th of a diopter, ensuring a final lens calculation perfectly neutralizes the eye's unique internal astigmatism and refractive errors. The Nidek OPD Scan 3 operates as a sophisticated 5-in-1 refractive workstation, capturing a comprehensive 3D optical map of the eye in under 10 seconds. Instead of relying on a standard better 1 or better 2 subjective exam, this machine harvests thousands of data points to create an engineering-grade profile of your visual pathway. For our 2026 computer glasses project, which relies on the IoT Camber Steady Plus technology, the digital RayPath 2 calculation engine, this data is a critical foundation. Now let's talk about position aware and its relationship to the digital RayPath 2 compute engine. Even a perfect 100th of a diopter prescription will fail if the lab uses default position aware measurements. Default data assumes a mathematically average face, ironically, a face that doesn't actually exist in the real world. Capturing accurate position aware measurements, specifically vertex distance, panoscopic tilt, and wrap angle, with the physical, customized Götti frame fitted to the face ensures that the lens is calculated for exactly how it sits on your face in reality. This hyper-precise telemetry, combined with the position aware data, is then fed into the digital RayPath 2. As a calculation engine, DRP2 surpasses older alternatives by mapping the natural dynamic rotation of the eyeball behind the lens. It mathematically compensates for the oblique astigmatism that occurs when glancing away from the optical center, resulting in a drastically wide intermediate corridor and almost zero peripheral swim. Now, let's talk about color science. When building a lens from Trivex, which is a material that we chose for its safety and its weight, we'll talk more about that later, one trade-off is its naturally lower ABI value. The ABI value is a measure of the subtle color bleeding or fringing at the edges of the lens. The Chromatic Aberration Reduction Technology, or CART, is a software module that plugs into the DRP2 engine to eliminate this. Standard lens calculations optimize light waves strictly for yellow wavelengths. CART mathematically aligns the focal points of red, green, and blue simultaneously, artificially boosting the effective ABI value of the Trivex material, which normally is 45, and completely eliminating color bleed. While the native ABI value of Trivex is 45, CART technology boosts it up to about effectively 56. That's about the same ABI value as a glass lens that you find in a microscope or a telescope. This pristine image is then sealed with Crizal Sapphire HR. For professional grade video engineering, absolute optical transparency is non-negotiable, and that's the use case that I'm working on. Cosmetic tints or flash mirrors destroy white balance and color grading accuracy, but the Sapphire HR coating provides maximum anti-reflective properties, ensuring the lens acts as an invisible window rather than a filter of any kind. Let's talk about the ultimate imperative, the multifocal workplace. This level of engineering is not a luxury. It is dictated by the topology of the desk and the digital workflow environment. The visual environment is a complex canopy of high-resolution, high dynamic range monitors, keyboards, and maybe video editing consoles and other control surfaces sitting at various distances from your cornea. Then there is the occasional need to look at an iPhone or read a paper document. Navigating this deep, wide workspace with a standard single vision lens of heavy, poorly fitted frames guarantees physical and visual exhaustion. Now let's talk about the fabrication plan, the dual layer biometric synthesis at Italy Optical. To bring this bespoke instrument into physical reality, the final phase of the workflow relies on the precision fabrication capabilities of the Italy Optical Lab. Just last week, IoT engineers deployed to the Italy Optical facility in Los Angeles, California, to upgrade the lens design software, specifically integrating the Chromatic Aberration Reduction Technology, or CART software plugin, that's required to facilitate the IoT Camber Pure Lens architecture. This upgrade ensures the lab possesses the necessary computational horsepower to process the massive telemetry files that we're generating. By pioneering this workflow, combining the Nidek's objective sub-micron 3D topology map of the eye, both inside and out, and refractive measurement, variable base curves of the Camber blank, the DRP2 engine, the CART optical alignment, and an ultra-lightweight custom-fitted chassis, we establish a definitive blueprint. It's a meticulous recipe that transforms a standard pair of computer glasses into a flawless biometric tool, paving a clear path for digital professionals to completely eradicate screen fatigue. This is the blueprint. We're discarding the century-old guesswork and replacing it with a workflow of absolute optical precision. By harmonizing the surgical-grade telemetry of the Nidek scanner with the computational horsepower of the DRP2 engine and the geometric advantage of the Camber blank, we're not just making a pair of glasses. We are fabricating a bespoke biometric prosthesis that actively neutralizes the microscopic flaws of human biology. This is the core of the Hubble telescope analogy. You aren't just magnifying an image, you're actively neutralizing biological visual noise.
In 2026, I am working on a very special high-precision project that will change the way you think about artisan eyewear. This is the Hubble telescope for my face.
This is how we take our visual endurance back. This is how we completely eradicate screen fatigue. But a high-performance optical engine is entirely useless if the chassis it sits on is flawed. Remember, if your frame slips down your nose, even by a single millimeter, or if the temple arms squeeze your head and cause a tension headache, the entire multi-monitor optical corridor we just designed collapses. That brings us to our next step. In episode 2, the chassis, radical modularity, and weightless fit, we're leaving the software behind and getting our hands on the hardware. We're going to dive deep into the Götti of Switzerland Perspectives collection and show you exactly how to defeat frame fatigue forever. I'll walk you through the exact architecture of my bespoke chassis, the DR02 frame, in a bold ruby colorway, accented by polished gold components. I'll show you why decoupling the facial geometry was critical for my fit, detailing the exact math behind my 54 eye size, the 17mm nose bridge, and the 153mm temple arms. We will explore how this featherweight radical modularity locks the lenses into an absolute unmoving position of wear, creating the ultimate zero gravity roll cage for your face. The blueprint is set. Now it's time for the foundation, and I'll see you in episode 2. Thank you for watching. Remember to like and subscribe. Make sure you smash that notification bell so you don't miss the episode 2 when it drops.